the record screen. Okay. Today I want to talk about types of reactions. Now I want to review with you what is a reaction. As you remember, a reaction starts with reactants, to products. Products are more stable than reactants, otherwise it won't happen. That is a reaction. We can kind of categorize them in 6 areas. Now, depending on what book you're reading, sometimes it's categorized in 4, sometimes 6. If you do it in 4, it's just a different perspective. It's all the same reactions, and they're almost identical in name. It's just the way they classify them is slightly different. I included this chart that I put together a while ago that kind of summarizes the reaction types. Now, we already mentioned one type of reaction type. And I want to go into detail on all 6 of them. Okay. First one is, the first 2 actually are very straightforward, and that's why I have them up top. A combination or synthesis and decomposition. They're almost the same reaction, only one is in reverse. A combination reaction we're combining 2 things or more. We're combining them into a single compound. Okay, now there's lots and lots of examples of this. This example here, we've got solid sodium, gaseous chlorine gas, and we end up making good old table salt. Good old table salt. Now, one of the reasons why there's so much salt in the earth is because this guy is very unstable. And you don't see much metallic sodium around. And because of that, anything it combines with usually is more stable than it, so it's immediately combines. But anyway, we have A plus B gives us AB. Excuse me. A plus B gives us AB. A plus B gives us AB. By the way, this reaction here is kind of a cool reaction. Is if you've ever been in a campfire and you or camping and you want to cook something on an open fire, the bottom of your pot is usually black, and that's because this carbon doesn't have enough oxygen when it burns, so it ends up being pure carbon, which is black. You can get rid of that one of 2 ways. You can use a scrubber pad, or you can subject the carbon, the black carbon, to a high temperature. And once you, like with a torch, and once you get that high temperature going, that carbon will combine with the oxygen and produce carbon dioxide, and the black will go away. This is why when you cook on your stove at home, the ratio of oxygen to your fuel is perfect, and you get no carbon. Anyway, A plus B gives us AB. A plus B gives us AB. AB. Okay, now the opposite of that is a decomposition, where you have something like AB, or in this case AX, and it decomposes to its parts. Okay, so for example, if we took water and put it in a tube with a battery, for example, one that will end up producing oxygen gas and hydrogen gas. So we're going from AB to A plus B. Silver oxide. AB gives us A plus B. So we have synthesis or combination. If we go the opposite way, we have decomposition. All right. Now, combustion. Formally, combustion is defined as fuel plus oxidizer yields oxidized fuel atoms. Okay. So organic reactants typically are carbon, hydrogen, frequently oxygen. So if we're taking, for example, this is octane. Octa is 8, so we have 8 carbons with all single bonds attached to the hydrogens. That gives us, it's called a saturated alkane. And we're gonna react that with oxygen. Okay, so this is going to be the fuel. And this is going to be the oxidizer. Okay, and we're going to yield oxidized fuel atoms. Okay, since this is the oxidizer, that means the oxidizer is going to combine with each of the elements of the fuel, which are carbon or hydrogen. Oxidized carbon is carbon dioxide. Oxidized hydrogen is water. So we're going to get carbon dioxide plus water. So whenever you start your car in the morning, you're going to end up with liquid water, not gaseous water, because the system hasn't warmed up enough to turn the liquid water into steam coming out the tailpipe. But you still produce water, regardless of the physical state it's in. Here we have oxygen being the oxidizer. And the fuel in this case is carbon disulfide. So the oxidizer is going to oxidize carbon, oxidize the sulfur, oxidize the carbon to carbon dioxide, oxidize the sulfur to sulfur dioxide. Now, many people don't consider ammonia as a fuel. It's used a lot in the rocket industry. For example, the X-15 rocket used ammonia as a fuel and liquid oxygen as a oxidizer. So again, this is going to be the fuel. Now, the oxidizer doesn't have to be oxygen. It could be other things. The bottom line is it oxidizes. It changes the oxidation state of each atom of the fuel when we have complete combustion. Okay, this is the most common type of combustion where you have some kind of a hydrocarbon, carbon, hydrogen, oxygen. For example, we did the same reaction with sugar. Let's look at sucrose, table sugar. Okay, first thing we need to do is balance this, okay? And then how many oxygens we have on the left? Oh, we've got 13. And how many we have on the right? We have 24 plus 11 is 35. Okay. So if we take 11 from 35, we end up with 24. So we put 12 here. That gives us 24 plus 11 is 35. So it's balanced now. So bottom line is the oxygen now is going to oxidize each part of the fuel. So we have carbon dioxide, water, and oxygen oxidizing oxygen itself doesn't give us anything other than oxygen. So, but that's the most common combustion reaction you'll see. Okay, now there are two reaction types that sound sort of the same, but they're not. One is called a double replacement reaction or an exchange. And the word exchange is nice because it sort of explains a reaction. And then we have and then we have a single replacement reaction. Okay, so we have double replacement, single replacement. Now the double replacement reaction requires the longest explanation. So we're going to tackle it first. Okay, so the deal is you've got two compounds. And what happens is you've got a swapping of the two. So we have a cation and a cation, and we have an anion and an anion. Okay. Now what's going to happen is these guys are going to swap their anions. So the original A stays here, but we get the other compound's anion. So instead of AX, it becomes AY. The B gets the original's anion. So it becomes BX. So these guys swap out. Okay. Now, one of two things happen. Nothing happens. Or we get a solid form. Fancy name for that is a Precipitate, sometimes it's abbreviated PPT. Okay? Or a molecular substance. Like water or gas. So either nothing or something happens. Typically, what happens is you'll get a solid form, like called a precipitate. Excuse me. Or you get something that is sometimes is not all that obvious, but there is a reaction between either this guy or this guy. And then gas is obvious because you'll see bubbling. Now, these are going to be either AY or BX. Not AX or BY. Okay, because these are ionic. But when we do the swap with the anions, something may happen or nothing may happen. Okay, and these are more stable, like always. That's what's driving the reaction. Is the solid compound is more stable, the molecular compound is more stable, or the gas is more stable. That's what drives the reaction. Okay. Now, the solid, the precipitation reactions. Now, we mentioned that before, and bring up the solubility chart, which is we talked about this last time, the solubility table. Sometimes this is very, it's written down in words. I like to use this one because it's very graphic and visual. It's black and white. If it's white, nothing happens. If it's black, that means a solid or a precipitate happens. Okay, so let's look at the first example here. We have potassium chromate. AQ means it's ionic. That means the potassium ions and the chromate ions are separate. Okay, and how do we know they're separate? Okay, if we go over here to the solubility table.
Like, who the fuck is this? This is so funny.
Hi. All right, so how do we know that the potassium chromate, the K2CR4, is soluble? Well, if we look at the Ks, notice the Ks are white all the way down. That means they're always, no exceptions, always soluble. Chromate varies, okay? The only time chromate is not a solid is if it binds with or is in the solution with sodium and potassium. So whenever you see potassium or sodium anything, it automatically means it's in ionic form. Okay, so if we look over here, what about this guy here, barium nitrate? Okay, that means we have barium and we have nitrates. Okay, barium, let's go over here to find barium. Here's barium, here's nitrate. So barium nitrates is also soluble. That's why they write it as AQ. Notice that all the nitrates will never form a solid. However, when we mix these two together, we have new combinations. The potassium and the nitrate can form now, and the barium and the chromates can hook up. So now we have to look at, again, the chart to see if anything's going to happen there. Well, we already mentioned that potassium is not soluble in anything, and nitrate's not. So that's going to stay AQ. Barium, chromate is down here. Black, that means it's a solid. Or PPT. So we take a beaker of potassium chromate, barium nitrate, we dump them together. We end up with barium chromate, solid. And potassium nitrate, aqueous. That means it's going to look just like water, no color, nothing. Okay. So we're taking two aqueous solutions, dump them together, and see the new combination. This is the deal, the new combination. The new combination could yield one of three things. It could produce a gas, it could produce a molecular substance such as water, or it could produce a solid. Okay, in this case, it produced a solid. Now, frequently, whenever we have a double replacement reaction, we want to talk about the net ionic equation. The net ionic equation is what is the equation of what happened? What happened here, we made a solid. So what's the equation for making that solid? Okay. We have barium plus chromate, and these are aqueous to start with. Okay, they're in solution. They're in solution. When we mix them together, we end up with the solid. So the net ionic equation describes product, which could be solid, any of those three. Okay, if any of those three happen, then there's going to be a net ionic equation. Now, sometimes when you dump two things together, two aqueous solutions, nothing happens. Okay, we dump two together and we end up with all white. That means nothing happens because it's now still in solution. So the net ionic equation. Tomorrow, I'm going to go into this in extreme detail. I'll give you lots and lots and lots and lots of examples tomorrow. Okay, so today I want to kind of introduce everything. Then tomorrow I want to really net it out in extreme detail. Lots of examples. Okay, I'm also going to provide additional worksheets for you to give you more practice. Now, I just want to tell you, these are a pain because there's lots of parts. You have to worry about the physical state. You've got to worry about balancing them, just a whole bunch of stuff. And again, I'll go into lots, excuse me, lots and lots of detail on that tomorrow. Okay. And that's what these steps are here. Okay. Let's look at, let's see, let's do, and these are all mnemonic equation. Now let's look at the second one where a molecular compound forms in a double replacement, which could be like water or something like that. Okay. These are usually acid-base neutralization reactions. Okay, so as an example here, we have HCl. And we have sodium hydroxide. And this is going to be a double replacement. That means the cations are going to exchange anions. So the H is going to exchange here, that place. And this is going to exchange here. We're going to exchange anions, okay? So what do we end up netting here? Okay, well, the first one is HOH. And the second one is NaCl. So H plus and OH minus forms water, molecular water. Sodium and chloride are soluble because remember the sodiums are always soluble regardless of what they hook up with. So that remains aqueous. Now the water can be either gaseous, liquid, or solid based on the temperature. So we're just going to put L here. We're going to assume this happens at room temperature. Okay, so the driving force here is water is very stable compared to the acid, compared to the base. Let's look at this other example here. And we have hydrochloric acid and sodium acetate. Okay. So that's H plus aqueous, Cl minus aqueous plus sodium aqueous. Remember now these are solutions. So we already know those are soluble. But the fact is it says solutions, okay? So So notice here's acetate right here. Notice it's soluble with everything. So the cations exchange anions. That means this goes there. This goes there. And the last one is on production of a gas. Okay. So we have H2SO4, which is aqueous. That means we have then we have aqueous lithium sulfide. And this forms the gas H2S, hydrogen sulfide, nice stinky stuff. And the lithium okay. So what is the net? I'm going to be detailing tomorrow this TIE, the total ionic equation, in lots of detail. Okay, so let's talk about the net. What happened? Well, we've got a gas formed. Okay, and what was involved in making that gas? Well, we had H pluses and we had sulfides. And notice tomorrow I'm going to talk about, is this a valid equation? It needs to be balanced. Same with this up here. You always balance equations. Okay. And as an exception, sometimes what you make forms of gas as an intermediate product. I'll go into detail on that tomorrow as well. Okay, so that's double replacement. Now, the thing about double replacement is that we exchange the anions. The cations exchange anions. And then we look at the resultant combination. Does a combination form a solid based on the solubility table? Does it form a gas? Excuse me. Or does it form a molecular compound like water? Okay. What if we start with something like a metal? With an ionic compound. And acids are ionic. What will happen is we will end up replacing electrons from one to the other. What will happen is electrons will go over to element B. And electrons will leave element A. So element A becomes cation. X is already an anion. Okay, so let's look at some examples here. Excuse me, gosh. Okay, so we have, ever since I took that stupid booster shot, I've been coughing with chickens. Anyway, so we have a metal here, sodium, okay? In a single replacement reaction, the possibility exists that the first element can lose electrons. Okay. So what happens is the sodium is going to lose an electron. Now, remember from when we talked about the periodic table, group 1, which is where sodium is, likes to lose 1 electron to become a full shell or a noble gas. Okay, so it likes to lose electrons. So what happens is it becomes sodium aqueous. And where does that electron go? It goes over to here. So this is going to be the A. Okay, let's look at calcium metal along with hydrogen chloride, hydrochloric acid. Okay, so again, we're going to lose electron, in this case 2, because it goes to Ca plus 2, because it's CaCl2. You know that's plus 2, because it's in group 2 on the periodic table. All right. Excuse me. So we have A, Bx. So A becomes the cation here. And B becomes it gains the electrons. So here we have H plus, Cl minus. So when H plus gains an electron, it becomes hydrogen element. We have two of them, so that forms hydrogen gas. Okay, so here we again, electrons are moving from the copper over to the silver. So when the copper loses electrons, it becomes a cation along with the nitrate. And then the silver ion here gains an electron and becomes silver metal. Okay. Okay, so here we have zinc losing electrons over to the copper. And this would be the A, and this is the Bx. Okay. So zinc loses electrons, it becomes the cation over here, +2. The copper goes from a +2 here to a copper 0. Okay, so let's look at the chemistry here. So we have copper, actually we have sodium metal, loses an electron and forms an A+1. In this case, it loses 1 electron. Here we have calcium metal, loses 2 electrons and becomes calcium +2. Copper metal, electrons. Zinc metal. So in a single replacement reaction, we have electrons being transferred, as opposed to a double replacement reaction where no electrons are transferred. Now, the question is, some metals like to lose electrons more than others. Why? As we talked about before with electronic configurations, to form a more stable electronic configurations, okay? That means full shell, full half shell, and this is review. This is a subshell. And that's what this does. So as we go down here, we have less stability. So what that means is by losing electrons at the top, we form a really solid full shell ion. At the bottom, for example, gold here losing 3 electrons, we really don't gain a lot of stability in that. Nothing compared to the top here. So if we have 2 competing metals where one is going to be over the other in terms of more stable, the one that's more stable will win out. Let's look at lead and copper here. Okay. Here's copper. And here is lead. What this says is lead becomes more stable. Remember, the higher on here, the more stable it is. So lead will become more stable by losing electrons than copper will be. So in a situation here, we're competing with lead and copper. Lead wants to lose electrons more than copper. Hence it does, it loses electrons. Boom. And who receives electrons? The copper. This is called a activity series, and sometimes you're asked to memorize it, but the bottom line is, why does the activity series exist? It is because of this here. We're forming more stable electronic configurations. It's important to understand why this exists. Okay. Zinc and lead. Okay. Now, zinc is way above lead. So that means it really wants to lose electrons over lead. So it's going to do it. And then those electrons that leave zinc are going to be given to lead. Let's look at this here. Zinc and magnesium. Okay. So in this situation, the magnesium wants to lose electrons more than the zinc. So it's going to stay right where it is, because it's Mg+2. So it's already lost its electrons. So have a nice day, zinc. It wants to stay the way it is. Aluminum, magnesium. Okay. The magnesium is above the aluminum, so it wants to lose electrons more than the aluminum. Okay. Magnesium has already lost its electrons, so it's going to stay that way. So nothing happens. Okay, again, I'm going to go over lots more of these tomorrow. This needs a lot of repetition on these guys. Okay. Up above, we talked about, and then we had a double replacement reaction. Sometimes we form a molecular substance such as water. That frequently will happen if we have an acid and a base. Okay, so the definition, there are many definitions of acids and bases. One of the definitions of an acid is a compound will ionize or dissociate to produce hydrogen ions. Example, anything with a hydrogen in it is capable of losing it. Question is, does it do it? If it does it, it's an acid. If it doesn't do it, it's a non-acid, a non-acid. Okay, so we have hydrochloric acid, nitric acid. Okay, so this hydrochloric acid disassociates or loses or ionizes the hydrogen, become H plus. What's left over is chloride ion. Here we have H. Does it ionize? Yes, it does. So it becomes H plus and NO3 left over. Okay. And notice this is in water. Okay, so that's an acid. A base is the same thing, only it produces an hydroxide ion. So anything with OH in it could be a base if it ionizes or if it disassociates. If it doesn't disassociate, then it's not a base. And there are strong acids, strong bases, weak acids, weak bases, non-acids, non-bases. Okay. The deal is when we mix an acid and a base. Remember, an acid has got an H and something. A base has got something with an OH. And this H is ionized, and this OH is ionized. When those come together, so the ionized H plus, we have the ionized OH. These form water. So we're left with then water plus what's left over. Oh, the Y and the X is left over. And this is called salt. So whenever we ionize an acid and a base, we get water plus a salt, which is a cation and an anion left over from the acid and the base. And this usually has lots of heat generated. Okay. So covered a lot today. So tomorrow I'm going to go over this again, basically with lots and lots and lots of examples. I'm also going to give you some extra worksheets as well on modules to practice. Okay, wasn't that fun, you guys?